Okay. Uh, Hello,
Yeah,
everyone. Thank you for joining in today. Today, we again have Raghunath sir with us from the Cheenta Math Olympiad team. We will be again doing an exciting problem from Indian National Math Olympiad 2023, and we will discuss it together. So, sir will explain the solution, and maybe I'll ask some questions just as students do, and we'll have some fun. So, you can grab a pen and paper with you as well. So, hello, Raghunath. Can you hear me?
yeah, yeah. Yes,
Okay.
sir. I can hear you.
Yeah, yeah.
So
Well,
this is the fifth problem of INMO 2023. So it states that you take a Euclidean plane, the Euclidean plane, and you mark some n different points. They might be collinear or non-collinear.
okay.
And for each pair of marked points, Gauss
Uh-huh.
writes down the number floor log d to the base 2. So what
Okay.
is this? Logarithm of the distance
Uh-huh.
d between the 2 points. Let's say the distance is d.
Okay.
Suppose say the distance is some 8. Okay. So
Uh-huh.
Gauss writes down log 8 to the base 2, which
That's
is
3.
3.
Yeah. Okay.
So instead of 3, he is 8. He is marking 3. So for
Okay.
each pair of points, he is doing this logarithmic value and the
So
floor of that.
basically, he's sort of joining all the pairs of
Exactly.
points with line segments
Exactly.
and then
He's-
reducing the length of each segment logarithmically.
Exactly. Instead of actual Euclidean distance, what
Yes.
Gauss is writing is just the logarithmic value, the floor function of that. So if like instead of you get logarithm value as 3, say you get some decimal, you just take the integral part of that, right?
Okay.
So
Okay.
that's what is happening, and you just do that for all pairs possible.
Okay.
So how many pairs are possible? Say n points are there.
Uh-huh.
Can you guess how many pairs of line segments are there in this
So
configuration?
if you have n points, so if we choose two points from those n points, every pair of
Exactly.
points will define a line, but they can also be collinear, so we don't know whether those lines are distinct or not.
But even then, if they are collinear, Gauss even write the distance for them also. For example,
Exactly, because we
if
will
they are
have
collinear.
different line segments at least. Yes, of course.
Exactly. So
So
this is not exactly about line segments, right? He just writes down the distance between 2
right,
points.
right, right. So he
So
will
in
write n choose two numbers.
exactly. So in total, Gauss writes n choose 2 numbers. We don't know
Got
how
it.
many of them are distinct and how many of them are identical. And that's
Right.
the question is asking us to bound. That is,
Uh-huh.
there are 2 and distinct numbers.
Right.
Okay. 2 and distinct numbers. For n like greater than 5, you always get that this n choose 2 n choose 2 is more than 2n. So 2n is a very good bound because even n choose 2 is having a degree of 2, right?
Right.
So
And square.
how uh, can we bound by 2 and distinct values? So what is the special property do you think of the Euclidean plane that might play a role here?
Uh,
Because
maybe.
what makes us like it can be unchoose to different distinct numbers, right? So
Right. Right.
what is the thing that is making us this? So that's where the Euclidean plane property comes into picture, that is the
Okay.
triangle inequality.
A
So
triangular
this is
inequality.
exactly, this is so special to Euclidean plane, right? So if you have 3 points, the triangle inequality says that, let's say the points are p1, p2 and p3,
Mm-hmm.
then the let's say this is d1, d2 and d3,
Uh-huh.
then the sum of any
Uh-huh.
two is greater than or equal to third side,
Right.
length of the third side.
Right. Right. Right.
So this special property about Euclidean plane makes us
Mhm.
think about this constraint. So I
Okay.
will sketch you how we can go about proving this, because this distances are powers of 2, right? So maybe
Yeah.
we will only consider the even numbers that Gauss writes down, because he's writing down integers, right? So let's only consider the even integers that he writes down. So
Okay.
I'm going to prove that the claim is there there are at most n minus 1 distinct even integers.
Oh, okay. So among
Do
the
you
n
see?
numbers that the Gauss writes down, if we just look at the even numbers that he writes down, you are saying that there can be only n minus one distinct such even numbers.
Exactly. Only n
Oh,
minus 1 distinct even numbers at most. The reason behind this is, um, if there are n or more distinct even integers, then
okay.
there is a cycle formed in the graph.
Oh, okay.
So
All right.
since the graph has n, we can consider this as a simple graph with n vertices, right? And for each of the integer that Gauss writes down,
Uh-huh.
consider the edge thus formed.
Okay. Okay.
So there are n points, and if there are at least n distinct even integers, then there are
Uh-huh.
at least n distinct edges, right, in the graph,
Right,
because
right, right.
each edge corresponds to each values. And if there are n edges in the graph with n vertices, it must form a cycle, which we will prove soon.
Okay.
But it will form a cycle, maybe like this. We will
All
take for
right.
example like this. So we are going to violate that there can be a cycle. That's the entire goal of this problem. We are going
Okay.
to violate that in Euclidean plane there cannot be a cycle whose
Oh, okay.
distances are. So suppose say that there are n distinct even integers, and
Uh-huh.
so there will be a cycle, right? So say that the cycle is formed by the distinct even integers.
So how can we
Like,
show that there is a cycle?
so what I thought was, first we will prove that at most n minus 1 distinct even integers, I mean at least n distinct even integers will be a contradiction. It's not possible. Then we will go about and proving that there will be a cycle.
Oh,
Or
okay.
should we, or shall we do the cycle uh, thing?
Any way you like. Yeah.
Yeah. So distinct even integers. Let's say the cycle is of length r. So the distinct even integers is 2k1, 2k2 till 2kr, suppose.
Okay.
And let's say without loss of generality that 2kr is the largest, is the is the largest value. Please note that this could be negative also, because logarithm value can be negative also.
Right,
But
right,
I
right.
just take the largest value, whether it is positive or negative. I just take the
Okay.
largest value as 2kr. And um, let's say that, so this edge corresponds to 2k1, and this edge corresponds to 2k2, 2k3, 2k4, and so on till 2kr. This is 2kr.
So just to make sure everyone is on the same page, these are not lengths of the
Exactly.
edges. These are log base 2 of the lengths. So that's why they can also be negative.
Exactly.
Okay.
The
Log
floor of
base 2
that.
is the part. Yeah.
Yeah, the logarithmic integer is these things. And remember, these are distinct as well. And assume
Distinct.
that 2kr is the largest value. I mean, the diagram
Okay.
depicts that 2kr is adjacent to 2k1, but that's not necessary. I mean, they can be in some order, and that's
Yeah, yeah.
fine. And let's say what is the distance that correspond to this edge. In order to see that, yeah, so floor of, let's say the distance is d, floor
Yeah.
of log to the base d, let's say d1, is what? K1, 2k1, right? So
Right.
floor means what? It's the you know, greatest integer less than the number itself. So
Right.
2k1 is less than or equal to log d1 to the base 2 is strictly less than 2k1 plus 1, because
Right.
2k1 is an
Absolutely.
integer. Now we found the bound for d1 at least, that
Right.
it is less than 2 power 2 2k1 plus 1, and it is greater than 2 power 2k1. Okay.
Right.
So can I say, I even though I cannot find d1 in terms of entirely in terms of 2k1, at least I can bound it above by 2 power 2k1 plus 1.
Right.
Similarly, 2 power 2k2 plus 1. Let's say this distance is d2 and this is d3 and this is d4, and add all of them,
Okay.
except dr, except the distance dr. You add all of them.
The largest
So
one. Yeah.
yeah, except the largest one, d1 plus d2 plus still dr minus 1. So it is bounded above by 2 power 2k1 plus 1 plus 2 power 2k2 plus 1 all the way up to 2 power 2kr minus 1 plus 1,
Yeah.
strictly less than.
Yes.
So you see where this is going, right? Because if we could prove that the sum of all these distances is less than the one last distance, you see the
Right.
triangle inequality is violating, right?
Yeah.
So
So
that's
here,
where this.
Raghunath sir is talking about the extended triangular inequality.
Hmm.
That sum of the sum of all the edges in a cycle will be larger than the one other edge which you did not consider.
Exactly.
So
So pictorially maybe like this. So if you take the sum of all these edges,
aha,
that must
that
be greater than this one last edge
one
in
last.
any, I mean, in the Euclidean plane. But this
Correct.
is
Correct.
going to be violated, as you will see now.
Aha. Of course.
So um, assume that out of this 2 power 2ki plus 1 is the largest. Some 2 power
Okay.
2ki plus 1 is the largest for some I
Aha.
in 1 to r minus 1.
Correct.
So if you take 2 power 2ki plus 1 common, you will get 1 plus. So what is the next value could be? It could be 2 power minus 1, right?
Right.
Please remember, every length, every like k1, k2, kr minus 1 are distinct. So at
Right.
least the next one should be at least 1 less than.
Right.
So the next
Correct.
one should be at least 1 less than that. So I'm
Correct.
actually making it finding the upper bound of this value again.
Got it. Yeah.
So this is
So
the
it will go
upper
on.
bound. Yeah.
Right.
So minus how many terms? R minus 1 term. So this is R minus 2.
Yeah.
Right? Because each of the distance is distinct. Now, using the GP formula, this is nothing but 1 minus 2 power minus 1. What's the number of terms? R minus 1 by 1 minus 2 power minus 1. Oh, just a small correction to this. This is whole square, because these are differing by at least 2, right?
Because they are even.
Exactly. So each power is odd. So if you take odd common, each of them must be differing at least by 2.
Right.
So this must be 2 power minus 2. So the common ratio is 2 power minus 2.
Right.
So now, just simplifying this, you get 2 power 2ki plus 1 into 4 by 3 times 1 minus 2 power minus 2 into r minus 1. Okay. Now again I will find the upper bound of this by
Uh-huh.
dropping this term. We shall
Right.
drop this term and say that this is strictly less than 4 by 3 times 2 power 2ki plus 1 for some I in
Right.
1 to r minus 1. Now
Right.
this is again strictly less than 2 power 2ki plus 2. Why? Because this is less than 2, right? 4 by 3 is less
Yeah.
than 2.
Of course.
So this is true. And what do we observe here? Since kr is assumed, 2kr is assumed to be the largest, this is
Mhm.
always less than or equal to 2 power 2kr, right?
Right. Because it's at least 2 more than 2ki.
Exactly. 2ki and 2kr are even numbers where 2kr is strictly larger than 2ki, which means at least the difference is 2. So this is less than or equal to 2 per 2kr. And do we say that? What do we observe from here? d1 plus d2 till dr minus 1 is strictly less than dr, right?
Right. Which is a
Because
contradiction.
this exactly, which is a contradiction for the extended triangular inequality.
Extended triangular inequality. Excellent. Yeah.
Exactly. Even I mean, this triangle inequality need not look like a polygon. Also, this can be of any configurations.
Right.
Maybe like this, and this last distance should be less than the sum of less than or equal to the sum of all the previous distances. But here it's contradicting that it is strictly greater than the sum of all distances. So hence,
Yeah.
what do I conclude?
Just to comment here, to that sort of non simple graph that you have drawn there. Uh, the reason some of the distances is larger than the final distance, the distance between the final 2 points, is because after all you are traveling through a different path, not the straightest path between the 2 points, right? So it will always
Exactly.
be so it doesn't even need to be a simple graph. It can be like, it can have overlaps and stuff like that.
Exactly. In the Euclidean plane, we know the straight path is the shortest distance. Correct.
Yeah, exactly.
Yeah. So that is getting violated here. And that's why I'm saying that there is no cycle with even integers.
So I have
Okay.
one more comment here. The 1 plus 2 to the power minus 1 whole square, the one that you just did, even if we just took the infinite GP series there,
Huh.
even
Yeah,
then we
even
would have
that is
gotten just
even then it's a strict inequality. Even then.
exactly
Yeah.
that will just give us a 2,
So
right? So
yeah. So it can just arbitrarily go
at large, yeah.
until that.
Anyway,
Yeah.
yeah. So continuing,
So we don't see any cycles of even integers. So do you agree that the proof just holds similarly for n distinct odd integers? Just a similar sketch would work for if there is a cycle with n distinct odd integers. I mean, any cycle
right?
of some length whose only logarithmic values are odd, you can just proceed by the same logic and you will get some series in even. Then you can prove it easily.
Yeah, it seems
So now we see, yeah, exactly. Now we see that there are at most n minus 1 distinct even integers and n minus 1 distinct odd integers
odd,
that Gauss writes down. Then that's all, right? See, we are only supposed to prove 2n distinct integers
right?
are there, and Gauss can write down only at most n minus 1 even and n minus 1 odd. So in total, he can write at most 2n minus 2 distinct integers,
Uh-huh.
which is less than 2n. But we are yet to prove one point. What is that? If there is more than n minus 1 distinct even integers, or let's say at least n distinct even integers, then there is a cycle formed in the graph.
Okay. Yeah.
Right. So only that is needed. So that requires some rigorous proof in graph theory. So either you can take up the result that is directly coming up from the graph theory, or you can do some work. Like for example, so let's first define what is a path in a graph. So path in a graph is a sequence of vertices, right?
Right.
Sequence of distinct vertices.
Yeah.
Like for example, x0, x1, x2, x3, x4, like that. And what is a connected graph? So a connected graph is that for any two distinct vertices, for any two distinct vertices in the graph, there exists a path connecting them. There exists a path connecting them. That is called connected graph. And what is a cycle? A path whose starting point and the ending points are the same.
Right.
x0, x1, x2, and let's say x0. So this is a cycle. So
Right.
with these definitions, we will do some claims and we will try to get onto that. So the first claim is, consider a simple graph G I will write the claim, then we will discuss a proof shortly. Consider a simple graph G with the m vertices. Where m is a natural number. If G is a connected graph,
Right.
with no cycles in it. Connected graph with no cycles in it. Then G has exactly m minus 1 edges. G has exactly m minus 1 edges. So this is our first claim. So what is being said here? If you have some m vertices, then if this graph G is connected and there is no cycle in this graph, then there are m minus 1 edges. So for example, there are 6 vertices, so 5 edges are there exactly. Maybe like this, 2, 3, 4, 5. So intuitively you can see, right? If there is one more, if at all there is one more edge, it's going to form a cycle.
Right.
So we will be in trouble. So there is also a rigorous proof, like considering just a short point on the proof. You just have to inductively consider the vertices one by one by one, and form a subgraph. And how will you form the inductively? How will you define the subgraphs? So if you take this subgraph, there should be an edge that is connecting this to the outside environment, right? Otherwise, it will not be connected.
Right.
Now, what you do? You just increase your subgraph size to this. Now there should be some more edge that is coming up here. Then inductively increase the subgraph size like this. And after this, you will be like exhausted with all the m minus 1 edges. And since this graph is connected, there exists a path between any two vertex, right?
Right.
So if you have any more edge connecting any two vertex, then you are forming what? An alternative path, which means there is a cycle. So between 2 points, if there are 2 paths, then there is a cycle. So that's why m minus 1 edges are there. Now going to our claim 2. it says that if G is a simple graph again, with m vertices, the same conditions, and m minus 1 edges, m vertices and m minus 1 edges and no cycle, then G is connected. This is sort of the other way around of the above claim. So how will I prove this claim now? You just have to take connected components of this graph. Suppose say that there are two connected components, and since there is no cycle, by previous claim I can say let's say there are T1 vertices in the first connected component, T2 vertices in the second connected component. So how many edges are there in my first connected component? By the claim 1, T1 minus 1, because the connected component is connected, right? And it has no cycle in it according to the claim 2. So T1 minus 1 edges are there in the first connected component, and over here you will be having T2 minus 1, and in total you will be having T1 plus T2, which is m, right? M minus 2 edges, contradicting to the fact that there are m minus 1 edges in total. And if there is 3 connected components, it will be m minus 3, 4, m minus 4 edges in total, contradicting our the claim 2 that there are m minus 1 edges. So there should be only one connected component in total, which means the graph G is connected. Is that fine?
Yeah, that looks good.
Right. Okay. So the claim 3 is the last one. So by this we will be done. So what this is saying, again, if G is a simple graph, if G is simple with m vertices, so now is where we are coming to that, m vertices and at least m edges, then G must have a cycle. This is what we are supposed to prove, right? G must have a cycle. So suppose if it has m vertices, just for an example, and at least m edges, we should prove that there exists at least a cycle. What you do, you just take out one edge randomly from somewhere. What will you be left with? M vertices and m minus 1 edges, right? Assume that there is no cycle in it. Okay. If you assume like that, then go back to claim 2. We observe that G is connected, right?
Right.
G is connected with m minus 1 edges only. So assuming that there is no cycle. So now if you add the edge that was erased before, what you are doing, you are creating an alternative path between those two vertices, because there exists already a path connecting them. Now since you are adding one more edge which was removed, you are creating an alternate path and which forms a cycle like this. And this is what I was mentioning, that there will always be a even edge or even cycle or odd cycle. When you have like n distinct the logarithmic values.
I think this is a very nice proof actually, because it also involved a lot of nice graph theory, and it involved an observation into how the triangular inequality really comes into play.
Exactly. That's the unique element of Euclidean plane, right? So that is a great use of that.
That is true. All right. Thank you, Raghunath, for this wonderful discussion. Maybe we'll come back again next time. For the
Sure.
viewers, I just wanted to say that if you like this sort of discussions, let us know in the comment section. We will do more of these. And if you want to do some exciting mathematics, you can also visit chenta.com for our Math Olympiad and other courses. Thank you. Take care. Bye.